folks. My name's Ralph. I'm here with Perforated AI, and I am so thrilled to welcome you all here for our inaugural California Hackathon. We ran one in Pittsburgh, which was cool, but this one's going to be even better. And I'm really so thrilled that so many of you made it out tonight and made it up here to this fantastic location. I want to thank Frontier Tower for giving us this space. It's been fantastic with them. Also, I want to give a big thanks to Weights and Biases. They were an awesome partner in helping us get started with this. And we've got some Weights and Biases people here who have cool stuff to tell you. I look forward to having them up here. Now, the hackathon, you may be wondering why you're here, right? Like, you're here to win stuff. And I'll tell you what stuff we have on the line. The first prize for tonight's hackathon. And remember, it's not done tonight. Tonight is just the kickoff. You have until January. But the first prize is 3,000 United States dollars, which we expect to be very valuable in January. and also 1 year Weights and Biases Pro membership, which will definitely be very valuable in January. We also have in second place $2,000 in a Weights and Biases Pro membership. Third place gets $1,000, so that is still very worthwhile. And then this is one of my favorite things about this hackathon. Rory came up with this earlier, and I just love it. We have Hackathon Inception going on, which is to say that if you use the model that you built here with our tech to win another hackathon, and you win first, second, or third place in one of those hackathons, and you show us the thing and it's an actual hackathon and not just like your cousin's hackathon, then we will also give you $500 for that, which, if you do an infinite number of times, will bankrupt our company. So I dare you to do it. Anyway, we're really excited. We got a lot of cool prizes and a lot of cool stuff going on. I want to bring up one more slide before I hand it over to our founder. And this is a slide of all the people who are involved in this hackathon. It takes a lot of moving parts to make this happen. And I'm not going to read everybody's name, but you should see their faces. Many of these faces are here tonight. These are very smart people who do all sorts of cool things. And I'm just so grateful that they've all decided to spend their time here with us and be involved in making the hackathon something that I think we're going to all be really proud of and have a lot of fun doing. Now, I would like everyone to please put your hands together and welcome the big brain behind the whole show, the founder and CEO of Perforated AI, Dr. Rory Brenner.
Thanks, everybody. Okay, so how this is going to work. Today, this is more of like just a workshop to kick off the hackathon. Over the next 2 months, this is deep tech research stuff. You're going to be training, which requires time. You can't train on the model in 3 hours. So tonight, we just want everybody to follow through the walkthrough and then have 3 hours of hacking, where at the end of tonight, once you go home, you shouldn't have to do any more real coding. This is going to be training, parameter sweeping, making your GPUs, putting that work. And January 5th, that is when your final projects need to be submitted. We'll then review them over the next 2 days, and then it'll be a virtual-only closeout on January 8th, because a lot of people are in from out of town for the PyTorch conference, so we won't make everybody fly back out to check that again. So now, moving on, we're going to talk about what we're doing here, what Dendritic Optimization is, before moving into how to make the best use of Dendritic Optimization with Weights and Biases, hyperparameter sweeps, and then go through the implementation walkthrough. So, a little bit about me. I am Rory. I went to undergrad at Carnegie Mellon for computer science, where I took this computer vision class in 2009, expecting to learn about how R2-D2 and C3PO see the world. And my professor just told me yeah, none of that stuff's real, computer vision is hard, then told me how Photoshop worked and the class was over. And I just thought that was crazy. Insects have perfectly functioning visual systems. How is the best AI this? Just awful. So I ended up getting a PhD in neuroscience, and while I was there, I developed a new way to build artificial neurons that since grad school I have now developed into a very easy to implement library that you can just download and add to existing PyTorch projects, and today we're sharing it with you. So to kind of go through it, as you all know, if you're here today, you know that AI is crazy right now. Everybody is talking about it, everybody is doing it, but it's also incredibly expensive. A single system just running 24/7, 365 on AWS can cost tens of thousands of dollars a year. Last year, ChatGPT used to cost 36 cents just to run a single query through their pipeline. And efficiency is so critical for large-scale deployment because even with all these costs, having these enormous models is still valuable. Llama just released this version, Llama 4 Behemoth, which has 2 trillion total parameters, and yet at many tasks, it's only like marginally better than these models that are so much smaller. But because every point of accuracy is so important, this new model is still very valuable, and lots of people are using it. And this idea that kind of like throwing more money and hardware and data at AI problems has been the foundation of AI research for a while now. And we think it's time to really kind of take a look at the core, take a breath, take 1 step backwards so that we can take 2 steps forward in a better and more efficient way. So most of the people in this room are AI experts and not bio experts, so I always like to start these talks with a little bit about history and biology, about what we're doing at Perforated AI and why this is so important. So as I'm sure you all know, modern AI products pretty much all use this technology called artificial neural networks. And because AI has only been at the front of the news cycle since the release of ChatGPT, a lot of people I talk to who aren't deep in this space think that neural network research is a modern innovation. But this original neuron was invented almost a century ago. It may surprise you actually that it actually predates electronic computers. This was 3 years before the first electronic computer, and that artificial neuron is still the same artificial neuron that to this day has millions and billions of copies powering all the AI that is starting to have this major impact on all of our lives every day. And that industry is long overdue for a new way to build. To understand why the modern neuroscience is important, I want to quickly tell you about the old neuroscience and exactly what piece of it has been proven wrong. Since the 1860s, we've known how biological neurons operate. Each neuron basically has 3 main components. Dendrites are the section that collect activation from presynaptic neurons. The soma is the main cell body where all that activation comes together. And then the axon sends signals downstream to other postsynaptic neurons. And in 1943, when this first mathematical model was created, scientists thought the decision-making of the neuron was only these 4 very simple steps. That presynaptic activation would be collected, there would be a weighted sum, and then if that sum passed the threshold, the only nonlinear decision was this neuron spike. And this combination of linear inputs with a single nonlinearity is how the original artificial neuron was designed. Other than these 4 simple steps in the actual mathematical decision-making, it used to be believed that everything in this complex biological cell only existed to allow these 4 steps to happen, because the neuron spike is the purpose of the neuron within your brain. These spikes will happen for lots of different reasons. In the visual system, there are neurons that are sensitive for particular shapes and line angles. In the motor cortex, they might be listening for a signal to move your leg. And there's even one study that they taught us about in our grad program that was sharing that neurons can also exist for very specific concepts in people. This group was doing single unit recordings of neurons inside the subject's brain and found that there was a Halle Berry neuron that just was active only for pictures of Halle Berry or also pictures of Catwomen or anything that this subject associated with Halle Berry. And the reason these spikes are so important is because neurotransmitter release happens when the internal voltage is high. What this means is that when the spike is at its peak, that's when this neuron is sending signals to other neurons. That thing that I'm in charge of, that's happening right now. This process of neuron-to-neuron communication is what allows our brains to do all the complicated decision-making they perform every day. The learning mechanisms to strengthen and weaken connections, neurogenerative techniques when the brain is first developing, and pruning forces to create and destroy synapses entirely are all pieces of the incredibly complex process to form the biological neural networks in all of your brains, which by adulthood is composed of about 86 billion neurons and 100 trillion synaptic connections between them. The idea that this simple formula is all that's required to simulate human intelligence has been the foundation of neural network research for almost a century. And one of the reasons is that for many of these years, neuroscientists continued to think it was accurate. Obviously, we've learned a ton about neuroscience since 1943, but for 70 of the last 80 years, nothing that neuroscientists have discovered has actually had impact on our understanding of the mathematical decision-making capability of individual neurons. Well, what I'm about to be teaching you is cutting-edge neuroscience that is just from the last few years. Seen here is your average neural network. Neurons pass together weighted inputs, when they then have a nonlinear function to pass it forward to go from data to decisions. Then for learning, backpropagation flows from the top to the bottom so that each neuron can adjust its weights to reduce its error the next time it sees the same pattern. This is the way that each individual neuron becomes a linear classifier, learning to identify low-level patterns that represent the high-level feature that they are coding for. So imagine now if you gave a neuron one extra connection, where that connection came from some magical node that was observing the same inputs, but that node only output a high value when the input pattern would be a false positive or false negative for the neuron's linear classification decision. Imagine how much better neural networks could be if every individual neuron had an assistant like this. Well, it can be done, and you don't need to make those nodes magic. The coolest part is that it's done in a kind of similar way to how we now know neurons operate in the brain. Modern neuroscience research shows that inside the dendritic tree, where the input of a neuron is received, there's a ton of additional nonlinear filtering that we didn't know about in 1943. And these aren't just random nonlinearities because of the imperfections of biological systems. These are nonlinearities that significantly enhance the decision-making of individual neurons. They're so important that there are papers coming out in modern neuroscience that actually argue that dendrites are the core building block of biological intelligence, and all the cell body even is this final hub where tens of thousands of dendritic decisions come together for one final decision. Well, the dendrite we have created at Perforated AI leverages this same ability in artificial networks to allow significantly smarter and smaller models to be created on the same data sets. When we discovered this function of dendrites and decided to create an artificial dendrite, we set two restrictions on ourselves, because we wanted to make sure that artificial dendrites were actually distinct from artificial neurons. The first restriction we set is that we wanted to make sure that dendrite nodes would somehow be outside of the system, but still able to impact individual neurons inside of the system. And the second is that something about these dendrites must be different. Whether it be the learning rules, the activation function, or whatever else, we wanted something about them to be distinct. So it wasn't just more nodes in a more complicated architecture. And one of the things we were really surprised about is that there actually, back in the late 80s and early 90s, was a lot of research on how to do these kind of additional non-backpropagation-based algorithms with single perceptrons that was never applied to deep learning systems once deep learning became a thing again in 2012. And so we landed on this thing called cascade correlation that was invented at Carnegie Mellon in 1989. The original paper has about 6,000 citations. It's very solid science, and we pulled that idea into deep learning. It's really easy to understand how it works by looking at some pictures. Of course, all a single neuron is capable of doing is drawing a single line to classify data as being above or below a line. So when you're looking at a data set like this, a neuron will be able to perfectly classify the blue data on the left and the red data in the middle, but it's completely missing the blue data on the right. Then, once you add a dendrite, rather than learning with gradient descent, these dendrites use a statistical correlation-based loss function. Dendrites observe the same input pattern as the neuron, but instead of using gradient descent, they learn to output a high value when the neuron is calculating a high error. In other words, they learn how to become outlier classifiers using the same data and the same supervised learning signal that the neuron already has access to correct it and make it able to make fewer mistakes. Then, once the dendrite has learned how to classify the data set into good patterns and problem patterns, it adds a single learnable weight to the neuron, so the neuron now not only knows what is the input pattern I'm observing, but also should I output a higher or lower value when this input pattern is coming from the area of the input space that my dendrite was flagging. And so now a neuron is able to perfectly classify a data set that is this simple. We capture this ability with our patent-protected algorithm called perforated backpropagation. This combines modern neuroscience and modern software to empower each artificial neuron in a system with artificial dendrites that are out of the system. To see how it works, you can first look at the dendrite learning on the right. The way dendrites learn is that backpropagation flows through the neurons just like before. But then, rather than adjust their weights at all, neurons just take the error that is calculated for them for a particular batch and perforate it out to an associated dendrite. The dendrites then use the same correlation-based learning rule to adjust their weights such that their output is high when the neuron's error is high. Once this has been learned as well as possible, we now go back to neuron learning on the left. Even with these new nodes added though, the network as defined by the flow of backpropagation doesn't change, because backpropagation doesn't flow through these new dendrites. In other words, neurons only care about other neurons when calculating their error. By doing it this way, every neuron continues to encode the same feature that it coded for in the original network, but because of the connection to the dendrites, it also has specifically learned how to make better decisions about the same feature. And by empowering every individual neuron to be better at the same role, perforated backpropagation also empowers the network as a whole. But for the most fun part, let me tell you about what these babies can do. You may have seen this from our original hackathon. We're now running our second. So the winner was the CTO of an AI consulting company in Pittsburgh who does a lot of work with his clients with the BERT natural language processing model. Across 8 different BERT architectures, he saw consistent improvements on the data set he was working with, getting between 3 and 16% reduced error on his data set when working with dendrites. What you're seeing here in this graph, the pairs of models with and without dendrites, where gray is the original model, and the higher orange bar to the right of it is the improvement that you saw when adding dendrites to the system. Our second place winner was a group of computational biology master's students. They were working with an amino acid classification system that had about 400 million parameters and an accuracy of 93%. They then shrank it to have fewer layers and fewer neurons per layer and reduced it to only have 50 million parameters, which of course had a huge hit on its accuracy scores. Then, by adding dendrites to that model, they ended up with a model that was still only 20% the size of the original while catching up to the original's accuracy, showing how much more efficient dendritic parameters can be than just throwing more and more neurons at your same data set. And circling back to our winner, he also applied this kind of compression technique to a BERT model, and he was able to shrink it by 90% while actually delivering slightly higher accuracy on that data set. After the hackathon, he actually continued to use this project and deployed it to Google Cloud to see how it would work in real-world settings. When maximizing for cost, the reduced model could process tokens 97% cheaper on a T4 GPU. And for those concerned about the environmental input, the AI cloud compute for this would also mean a 38x reduction in carbon footprint of running that AI model. And when simulating for edge devices, by running this model on a CPU-only instance, the reduced model was able to process tokens 152 times faster. As fast as the original would have required 11 GPU instances to do. We have had successful results on all of the use cases listed here. We've done image classification and segmentation, time series forecasting, time series classification, and graph networks. We've improved ResNets, transformers, UNets, recurrent nets, and CNNs. This list is ever expanding, and we are confident this algorithm is compatible with anything built using PyTorch, as long as the right choices are made about how to integrate it with your original project. And today is your first chance to try this tech out on your models. To facilitate optimal results, we are absolutely thrilled to be partnering with Weights and Biases. When training a project like this, there are many hyperparameters to choose from, and Weights and Biases really helps you navigate all of those decisions to find the best possible outcomes. Well, Perforated AI's dendrites add a ton of extra hyperparameters that, of course, nobody has any experience with. So to have the best outcomes, Weights and Biases Sweeps is going to help you make significantly better final decisions the first time you're trying out this project. So without further ado, please give a warm welcome to Mo to tell you about Sweeps.
Good day, everyone. Thank you for being here. Excited to be here myself. My name is Mohammed. I am an AI solutions engineer at Weights and Biases. And effectively, my role is to make our customers successful with our products and services. Today, I am joined by my colleague Sam. He's in the back. He helped really orchestrate all this. He's extended the invite to me. Please feel free to talk to him. He's wearing a really cool fire jacket that he himself designed. So, just to kind of show of hands, who here has heard of weights and biases or have used this? Wow, okay, wonderful. So for those who have not heard of us, Weights and Biases is an AI developer platform. And effectively what we do is we want to help you build models with confidence and also provide you an observability layer over your experiment runs, being able to track experiment results, the history of your experiments, and be able to collaborate amongst your team with a unified workspace and consider it a single pane of glass. So today I'm going to talk about sweeps. And before I do that, for those who don't know what weights and biases is, I'm going to orient you to the left-hand side of our screen. We first started with our models offering. That's really what our core components are. First of which is our experiment tracking. You'll be able to train, fine-tune, and run your experiments. And that's supported by artifacts. Artifacts effectively are block storage types to allow you to track any data set asset that you used. So for example, whether it's you're using data sets, maybe you're creating model checkpoints, so there's files that go into your training runs. You'll be able to track it with artifacts and also version control it, and then build lineage on top of that. Now in addition to that, supported by tables. Tables allow you to take any data, effectively visualize it, interrogate it, work with it within the workspace itself. And we won't be touching on that today, but I highly encourage you to kind of check it out as you're hacking along. And then lastly, what we're here to do is talk about sweeps. Before we do that, I'm going to point you to the right-hand side. Obviously, for the last couple of years, there's been an explosion, large language model development, agentic application development, and we've developed a new tool just to address the needs of the new research based around that, which is giving you an observability layer over your Gen AI application development. So now, weights and biases, our philosophy is we want to make it easy for you to be able to use our platform. We're completely agnostic. You can run it with on any environment of choice. All you need to do is start with 3 lines of code. All you have to do is pick a Solomon beat, initialize your experiment, effectively telling weights and biases, I am ready to track my experiment results. And then you're going to pass us a dictionary of key value pairs, which are your metrics and the results you want us to track. We'll do the rest for you. So now, what is sweeps? I think most researchers here have at one point in time tried to optimize on hyperparameters. And naturally, that is a workflow where you're continuously iterating on many combinations and you're trying to find the most optimal combinations for the best results of your experiments. And that's what sweeps is intended to help you do. It's a scalable, customizable tool for hyperparameter search and optimization. And some of the key features is we're going to automatically run those experiments for you in your environment once you set up sweeps. In addition to that, we automatically, out of the box, we're going to support 3 main search strategies, which is grid search, Bayesian search, and then random search. And then these 3 methods help you effectively get this range to help ensure your best method for your projects and resulting outputs. And lastly, one thing about sweeps is we want to help you save on time. We want you to be able to automate that tuning process. Let it run, let it play out, and then you come back, you have this really rich populated UI with all your experiment results that I'll go into very shortly. But now I kind of talked about sweeps. I want to make it easy for you. So there's 4 things that you have to do to set up a sweep. First is you just have to create a sweep configuration file, whether that's in a Python dictionary, or you can create in a YAML file. And effectively what this is, it's going to outline the parameters and the strategies that you want to sweep or run experiments against. Second, as part of that configuration, you're going to define that search strategy that I mentioned earlier. So grid search, you're going to test every single possible combination that you define. Then there is random search, which is going to do a sampling across your hyperparameters. And it's surprisingly really effective, especially for these larger search spaces. And it helps you really hone in on most influential parameters. And then lastly is Bayesian search. It's more of a probabilistic approach against the region. You maybe have a region of space that you really want to optimize against, and over time, iteratively, Bayesian sweep is going to really direct against that search space to help you optimize and find that parameter of choice or the value of choice. And then one thing I'd like to point out, because we'll get into that, is if you're going to choose random or Bayesian search, they will run forever. It is up to you as the user to control a sweep. You can define how many runs you want to execute at any time, or you have full control over being able to go into the UI, pause, start, resume a sweep, or you can do it also programmatically. Now, the reason I say that is, if you're working in a constrained compute environment and you just let it run for days or weeks, you're going to be shocked when you come back and realize, oh, oops, I just ran 1,000 experiments and burned X amount of dollars. And then third, you just need to create the sweep object. So all you have to do is create a sweep ID, and you're gonna create and name that sweep and then assign a project to it. And then lastly, a sweep agent that you're going to run on your compute environment of choice. And that's all you have to do to set up sweeps using weights and biases. Now, to kind of summarize that architecture, within weights and biases, for those who know, there's the concept of a project. So within that project is your collection of experiments. Within that project, you're going to define your sweep, your hyperparameters for that sweep, and then lastly, you're running your agents. Agents for sweeps run on, as mentioned, any local environment, and you can run sweeps in parallel. So anytime you call a like sweep agent command, we're going to look at that queue of hyperparameters that you define. It's a FIFO, first in, first out. We'll just start pulling parameters. As I mentioned, any training infrastructure of choice. Now I'm going to go into the workspace. Let's see. Got that. So there's a notebook that we're going to reference later for you to run through, but the reason I want to bring up this is to kind of orient you to what the weights and biases workspace looks like and how to actually go and look at your results. Now, here in the top bar, it's your entity is your team name. It could be a personal account or a team account. And then within that is your project that you define. And within that project, on the left-hand side, there's going to be the workspace, which is the collection of all your experiment results. And look for the sweeps tab. Now, here is all the collection of all the sweeps that I've executed over the last week. As you can see, here is an estimation of the number of runs that were executed as part of that. I paused it after a couple of runs. You can interrogate any of those sweep results by just selecting one of them. And here, these are your numerical charts, basically your scalar metrics or metrics of choice that you're tracking against. What I really want to orient you to is this panel here, which is called the parallel coordinates plot. And let's see, I'm going to expand that. All right. So just a very basic example. Each of these columns represents a hyperparameter that you ran an experiment against. On the far right-hand side is what we consider the target metric that you're trying to optimize against. So in this case, for those who might not see it, this is test accuracy. So effectively, each of these lines represents the set of hyperparameters and then the resulting output. And what you will eventually see when you run many, many iterations is this beautiful chart that allows you to not only hover over multiple lines, but then also go down and, if you want to, select a specific region to filter against. So maybe you're trying to optimize or minimize a specific metric. You're going to go into the workspace and work with the data that way. Here we have a parameter importance chart. It's very simple. It just uses a random forest classifier to look at the configurations against the metric of choice, and it'll tell you which of the configurations are most optimized and contribute to the best resulting score. There's also this little like magic wand at the top that will automatically kind of help guide you against that as well. Now, I'm going to go back to my presentation. So it might take you a while to get used to the workspace. I'm here, please feel free to grab me. I can kind of drill down a little bit deeper with you just to kind of show you the ins and outs of that. But before I wrap up, one of the things that I want to talk about is some kind of guidance around how to set up your suite. I think one thing that most folks do is they have a tendency to just kind of want to throw everything in a suite. And what that does is it overwhelms them. There's just too much information. They're not sure how to progress once they start running their experiments. So what I have to say is, don't change too much too soon. Start with your initial model. Change maybe a few hyperparameters at a time, and with each one, give them enough range to explore. And on top of that, usually start with the easy stuff: learning rate, batch size, maybe the optimizer that you're using. Based on those results, then come back to it. Once it's dialed in, move to maybe your architecture, number of shapes, like the size of your model. And then from there, moving on to like the third layer of more detail, finer detail, like weight decay, learning rate schedule, etc. So kind of taking it more like a methodical process as you approach sweeps. And then, as I mentioned earlier, we want to make it easy for you to just run all these experiments at once. Let sweeps do the work for you. Don't try to overmanage it. Don't try to come to the workspace every 5 minutes, look at the results, try to refresh the page. My recommendation is set constraints. You can specify the number of runs that you want to execute the sweep against. Maybe you start with a few, 5 or 10. Let those run, come back, analyze the results, and then once you're there, write down what you actually learned. Think through that process. Think about what you want to do next. Maybe you want to go back and resume this sweep, and maybe you want to resume it against a new set of hyperparameters. Maybe you want to start an entire new sweep, and we're going to give you that flexibility within weights and biases to be able to do that all at once. And that's how you kind of make that steady incremental process, and I call it like babysitting the process, so to speak. Now finally here, just to get started, for those who don't have a weights and biases account, just go ahead and scan the QR code, or you can go to the link for sign up. Your team name is going to be at the bottom of your home page. You'll be directly oriented to that. And then for your API key, when you authenticate against our API, you just go to 1b.ai/authorize. And then I provided a link at the bottom for the sweeps documentation, which is going to run through a lot of examples, and it's going to walk you through all the configurations that you need to do. Thank you so much. Looking forward to talking to you guys all later, and best of luck.
Okay, this is kind of random. I have a little bit of fun extra news. Y'all like training models, right? Yeah. Do you like compute? Do you like GPUs?
Yeah.
Okay. Many of you may know this, but Weights and Biases was acquired by CoreWeave like 6 months ago. And CoreWeave is a company that is best known for having a fuck ton of GPUs. So, I imagine most of you like training models. I just found out that I can offer $5,000 of compute credits to one of the winners of this hackathon.
Woo!
So I know, yeah, round of applause.
H200s.
Yeah, so I know it's a 2-month hackathon, it's a long thing, but if you get to actually train your model, get it out the door, then you have a chance at that $5,000 in compute credits, and then you can train bigger, more beautiful models. Yeah, if you have questions about that, come find me or Mo. Cheers.
Thanks so much, guys. That was awesome. Those sweeps are super cool. I still can't get over how sweet, I forget what you called it, the squiggly graph. It's amazing the first time I used it. We're now going to get into our implementation walkthrough. Let's start the hacking. So the goal of the remainder of today, just as a reminder, is to get everybody in this room, by the time you go home tonight, have your projects fully implemented, so that over the next 2 months, the sweeps are doing the work for you, and there will be minimal actual coding required after you leave today. So leading up to this hackathon, everybody should have chosen a PyTorch project that you want to optimize for the next 2 months. Now is the time to pull that up on your laptops. On the left is this QR code that will take you to our open source repo. Here you're going to be able to just copy paste everything that I'm about to show you on the slides, so you're not frantically typing with my font choices up here. You don't have to just go through it very slowly. Also, Perforated AI has 2 different versions of Dendrites. We highly recommend you work with both to see what works best for your system. If you'd like access to our secret sauce Dendrites, scan this second QR code here, which is going to take you to a form, which will send you what you need to get started. I'm going to leave these up on the screen for a little while so everybody has time to scan them. And then once we go through the remainder of these slides, try to code as you go. There's going to be 3 sections. The first is the base implementation, the second is the sweeps, and then the third is going to be a little more complicated, so for that one, no longer will be expected to code as you go. This one, for the third one, please don't just blindly copy paste. There's going to be some of these things that require a little bit of thinking based on your specific model, but I will try to call these out and have some short pauses when you get there. So to start, just do a very basic pip install Perforated AI, pip install 1B, and if you would like access to the second version of Dendrites, also do a pip install Perforated BP. So we're going to start with the most basic steps, just the imports. So at the beginning, just do Perforated AI install import globals as UPA and utils as UPA. And again, these are all at the very top of the API. You should be able to just copy paste these, put them right into your file. Next is the initialize step. This single function, initialize Pi, sets up everything behind the scenes to set up the scaffolding to add Dendrites to your system. You will need to pass it a model. You also can pass it a save name if you would like to specify a different save name where your output files will be saved. If you don't specify a save name, then it's just going to overwrite all of your experiments when you run the next experiment, where sweeps will still keep track of what happened, but you won't have any saved model files on your local machine. Next is the value maximizing score. This is one that you shouldn't just copy paste. Please take a second. If you are trying to maximize an accuracy score, set this to be true. If you are trying to minimize a loss value, set this to be false. Next, there are some extra steps that we encourage you to use when setting up your optimizer and scheduler. If you do perform the more complicated steps, then the backend is going to automatically pick the best optimizer settings to use each time the Dendrites are added. If you just do these yourselves, you also can call set optimizer instance, which will point the tracker to your optimizer, but it won't automatically find it for you, and you might have to do some additional scheduler settings yourself. So basically, if you do want to do the automatic selection, instead of passing the Pi tracker, the optimizer itself, you tell the tracker the type of optimizer and scheduler that you would like to use with the functions set optimizer and set scheduler, and then you define a dict which has the parameters that the optimizer and scheduler will use, and call the function setUpOptimizer with those dicts. I'm going to give you another second to walk through this because some of these take a little time. It's not as simple as just copy pasting, and we don't want people to be super rushed. Next is possibly the most important function, add validation score. This is the function that determines when it is time to add Dendrites. So basically, depending on your settings, rather than just early stopping when your validation scores stop improving, this is when Dendrites can be added so that you continue learning more on the same data. This function is going to return 3 variables: model, restructured, and training complete. If restructured is true, that is because Dendrites have been added. In this case, the model that gets returned is a new model. So you should also copy paste whatever code you are using to initialize your optimizer and scheduler. So also it is in this if statement so that your new optimizer and scheduler will point to your new model when you continue back to your training loop. If training complete returns true, it's time to actually perform early stopping and exit your training loop. To note, this is the only time you should exit your training loop. It's optimal to remove fixing training for a certain number of epochs, and instead only exit once training complete has returned true. A lot of early users don't do this step. tell us their system isn't working, and then we look at their graphs and says you quit before you actually added any dendrites. We don't want that to happen to you. If things are working properly, this is what your graph should look like. A folder is going to be generated which outputs a bunch of graphs and CSV files, and one of them will be a graph that just has the same name as the main folder. On the top left of the graph is something that looks like this. And the only thing that you need to take note of is the vertical lines. This vertical line is what is happening. It's like every epoch that a dendrite is added, that is when a vertical line is drawn. If you don't have any vertical lines, no dendrites have been added to your systems. And as you can see, when things work properly, each time that a dendrite is added, there's kind of a quick dip in accuracy as the system adjusts to the new architecture, and then it eventually surpasses the old accuracy and gets a little bit better every time a dendrite is added. So now that has been it, that is everything you need to get dendrites initially added to a simple system. And now this QR code will take you to another step of our repo, which is how you get started with dendritic sweeps. This will sweep over the most impactful choices, but if you take a look in the Perforated AI folder in Global's Perforated AI, you'll see additional hyperparameters that you can add to your sweeps if you think they will have significant impact on your systems. Step one, as you have already seen, is the import and the login. You must define the config and metric like you just discussed. For now, this can just be copy-pasted from our repo in the weights and biases markdown file. Next is the parameters to sweep over. Also for these, just copy-paste them directly. For the sake of getting started, we're not going to go over every single value, but ask us questions on the Discord if you have specific questions or have additional values you think might be important for your system. Then set up the sweep config and ID using the parameters dictionary, like Mo just told you about. This next parameter is called cap at n. Take a second to decide whether or not you want to include this. What this setting basically does is if it is set to true, it sets your dendrite training to never take longer than your neuron training. This is sometimes really important because sometimes you might have 10 neuron epochs and then 500 dendrite epochs, and the first 10 are the most important, and eventually it's best to let it run the maximum amount. But when you're first getting started and you just want to prove the proof of concept on your systems, setting this to be true can make your experiments run much quicker. So often we recommend it for first-time users. Next is an update to the way that you actually run your script. Rather than running directly from your main, you should tell the weights and biases sweep agent to run the run function and then run the main inside that run function. This can also just be copy-pasted directly from the repo. Now, in your main, you need to actually use the parameters for this sweep. Your main should take in the run as the parameter and then immediately extract the config from that input variable. Then for each config setting, just make sure that you put it in the proper place. Most of these are set within the Perforated AI constants object inside the global's Perforated AI file that can again just be copy-pasted right from the repo. But if you are configuring extra settings like width and dropout that will need to be adjusted by your own system, this is how you get access to those variables. And then if you would like to define names for each of your runs, this is the way that I personally like to define a name string that just is an accumulation of all of the config parameters for that specific run. And lastly, if you need to actually pass, you have to actually pass weights and biases your score after each epoch. This is done with run.log for your train, test, and validation scores. And make sure that the validation score you use here with your weights and biases login is the same validation score that you use for that dendritic add validation score function. And for simple networks that have convolutional and linear layers and nothing else, that's all there is to it, and you could already be done with your implementation. But for more complex networks that I'm sure many of you will be working with, there is some more optional configuration settings that I want to go over. But these are definitely more complicated, they require some thinking, so at this point I would not try to do this live, I would just pay attention and then ask us questions, either come to the front or ask on Discord, and we'll help get you started. And also, if you do have problems with this, the dendritic code will print out errors and warnings and suggestions, and you won't just have issues and not be aware of them. But please do not just ignore these warnings and errors. They're there for a reason, and if you want to maximize impact, again, listen to them, read them, and make the corrections that they recommend. And so the first step is conversion lists. In the earlier talk, we kind of described how this is neuron nodes and dendrite nodes, but under the hood with PyTorch, what's actually happening is it's neuron modules and dendrite modules. And so it's often going to be the case that you might have better results if you convert the linear layers all the way at the depth, or if you convert higher up layers like a full bottleneck block of a ResNet all at once. So to do that, you just add those modules to these lists. Modules to convert lets you add them by type, module names to convert lets you add them by name, and then to make sure that you are not just accidentally ignoring something that wasn't done intentionally, you should also add the remainder of your modules to module names to track so that the system is sure that you haven't just forgotten anything by accident. And then module IDs to track lets you specifically say, I don't want to convert these modules even though they're in the above lists. This is what you can use. Often there will be maximum impact if you add dendrites to the final output layers. So if you want to really maximize your parameter efficiency, you might want to add the IDs of the lower layers of your network to just be ignored and not add dendrites everywhere. The next thing to make note of is that normalization layers can have a very significant impact on dendrites if they are outside of the dendrite modules. So for this reason, you should always try to add wrappers around any modules that have batch norm layers in them. But we also have created this PySequential block that lets you just kind of like do that very easily. Just basically create a new one and then pass in the layers that you want to group together, and we will automatically convert anything that is wrapped this way. Again, if you don't wrap your norm layers, a warning is going to get printed out. Please don't just ignore it. This really does have significant impact on the ability of dendrites to improve your systems. Next, we have input dimensions. So default settings with just convolutional and linear layers, it gets processed automatically. This basically is just telling the system, hey, I have some X dimensional tensor, which is the neuron index. So as you're doing, convolving and multiple batches, it lets you know which should be kind of correlated for and which ones should be like the convolutional dimensions. Often this is not consistent across your entire network. So at the beginning, you could also call set this input dimensions that says, hey, for this particular module, use a different setting than the default. This must be called after initialize pi, and will again give you a warning if you don't do it correctly. And finally, most of what we've gone over so far is relatively straightforward, but the thing that is really complicated is what's called a processor. One of the kind of assumptions of what's happening under the hood with the dendritic modules is that you're correlating the error tensor with the output tensor of the dendrite. And so if you have multiple tensors going in and out of your modules, you need to create this processing class to tell the dendrites what to do with all the extra tensors. We have this set up for something that's just multiple inputs where you want to just ignore 2, 3, 4, 5. And we also have a default that is created for a GRU type of architecture where you want to save that second one and use it on subsequent passes for the dendritic GRU module. But again, this is something that's quite complicated. We're not going to go over it in detail live, but please let us know your use case, what your module looks like, and we'll help you build a processor so you can use it for your architectures. And that's pretty much it. But so now there's also 4 pieces of just general advice I want to go over. First, regularization is super important. If you're already overfitting and your training accuracy is way higher than your test and validation accuracy, dendrites are just going to make you overfit even harder. So you should probably, if you're in that case, you should add some dropout layers, you should use smaller networks, do weight decay. There's lots of regularization options out there, and all of them will help you. Once your training and validation scores are closer together, and training better means validation is better, then dendrites have much better impact. Next, I would definitely recommend when you're first doing the implementation tonight, before you go home and are actually running your experiments, I would start with a smaller data set so you can iterate quickly and make sure that the dendrites are being added properly while we're here to help you debug. Next, something that is not included in the sweeps is what modules to wrap. This is something that kind of has to be done by hand, so just be aware, it might be good to start just doing linear and convolutions, but you should definitely do some experiments with wrapping different layers of modules. And then, just to reiterate, because this is worth saying many times, do not just ignore the warnings that get printed. People do this all the time, they then tell us things didn't work, and we ask them to show us their output, and we see all these warnings, and we're like, hey, that's why it's not working. So if you get a warning, please fix it, read what it says. If it doesn't make sense, come and talk to us, and we will help you walk through how to fix it. And yes, please ask us for help. We want you to succeed. We are here to have you optimize your models. We are not going to make you lose points if you bug us. The winner last time, this first place person from Carnegie Mellon, asked us more questions than anybody else by a very wide margin. So if you want to win, please ask us for help if you're not seeing improvements. Ask us, suggestions, send us graphs. We are available in person for the next 3 hours. We will be available via email and Slack. And with that, we're now going to take 15 minutes of questions, general advice, and also we'll have judges up here who can do a quick intro about themselves and what they're here for, what they're looking for in the prizes. So feel free to ask about anything, implementation, theory, VC questions, weights and biases questions. Everyone's just going to be up here. So yeah, we got 15 minutes. Please give a warm welcome to everybody who is here to pass judgment. Wait, do we have a...
Yes.
It's over here. Test it. Hi everyone, I'm Ryan Green. I'm from Alpha Intelligence Capital. We are a deep tech and AI focused fund, investing through Series B, starting at seed. We are a global fund interested in any kind of interesting use of AI. I think when it comes to judging, I will be looking for everyone heeding the error warnings. And I will be looking for commercial applications as well. I want to see you guys connecting this to problems in the real world.
Hi everyone, I'm Prithvi. Wow, that's loud. All right. Hi everyone, I'm Prithvi, research scientist, principal investigator at Siemens. I do work in robotics. Predominantly my interest in a lot of these applications is whether or not you can reduce data requirements for a lot of these models, especially for VLAs or any robotic applications. This is a very pressing commercial problem because these models just require a ton of data that we don't have access to, especially in manufacturing for the sake of argument. So figuring out ways to reduce those, I'd be looking forward to seeing if any of you guys can, make efforts to that end. And yeah.
Well, come on over.
Yeah, sorry, give us space.
Hey everyone, my name is Beyond. I'm a senior systems engineer at NVIDIA. Nice to be here, and my general piece of advice would be that making your narrative clear in a hackathon does matter, and I think talking about what was your thinking, why you tried what you tried, what exactly the delta was clearly. I know a lot of people are going to be going for accuracy, but connecting that to why the delta is important in the specific problem space that you're working on can be really impactful, even if it's a small gain.
Hey, first up, thanks to the Perforated AI team for having a note tonight. My name is JJ. I'm an early stage investor at a firm called Side Door Ventures. We're pretty generalists, but we definitely bias towards the fringe. So think things like orbital drug factories, next generation semiconductors using reversible logic gates, and implantable cancer therapeutics. So I'm excited to see what everyone's working on today, and but particularly if we're working on something a little fringe or weird.
Sweet. Erin Janacek. I'm one of the co-founders with Rory and Ralph. I just left McKinsey, one of the big bad consulting firms, and so I do love money and the idea of money. And so I would very much encourage you all, as you post testing, as you think about how to bring together the narrative, to trace it to the potential economic impact. That is what people are getting so geeked about. That's what all of the investors are thinking about when they try to, do the market sizing. And so for any one use case, say you're doing like a robotics thingy and you're like, I can make a much smaller chip in this drone and that'll save me X amount of energy per trip times 1 million trips a year or whatever. Just do some fast math like that. It's gonna be super inaccurate and that's fine. And we just wanna hear an estimate, but trace it to dollar value.
Hi everyone, back again. I'm Mo, AI Solution Engineer at Weights and Biases. So I typically work on a day-to-day with lots of different customers, talking about video game developers, chip designers, so I've kind of seen it all to a certain degree. And when it comes to hackathons, one thing that really excites me is just something, a unique idea that's applicable in the real world. And what I mean by that is an opportunity to just take something and then be able to not just only, I don't want to say sell it, but be able to come to me and talk about, one, how you set it up, what is the problem you're trying to solve, and then how it could help me, whether it's on a day-to-day basis or a long-term solution, something that I could use at work, or maybe I could use on a personal level. And that's what I look for, honestly. But I definitely will, like, whatever you guys have to bring up, and we're looking forward to it. Yeah.
One more.
Hi everyone, I just arrived just on time. I'm glad. So my name is Arisa. Very nice to meet you. I'm a part of JPU Ventures. We are based in San Mateo, so it's like 30 minutes, sometimes 1 hour away from here. I know it's kind of far away, but we have accommodations, like it's 8 floors and then 100 founders living together. So we sometimes host the hackathon, and we also do some accelerators program, residential program, and then actually I brought some founders from Draper ecosystem. So and if anyone is interested, we will be around that area, and now we are having a deep tech program happening. So actually more than 150 founders are living there. It's a little bit chaotic sometimes, but I would say it's also fun. But looking forward to seeing the project, and then as I heard, it's something that is unique, but also something that not just within this environment, but someone that who are able to explain what you are building in a simple way and precise. That is really important, because sometimes you're really a hardcore techie person, and then when it comes to explaining, making sure the other person is also understanding with you. So understanding what is the terms, what is not the terms, and then how we can simplify the concept. In that way, it will be easier to spread around and then get more attention for it. But very excited about it.
All right, we'll do this classic style. If you got a question, raise your hand.
Oh, that guy.
Where do we find the slides?
Oh, yes, we will post those to Discord very shortly. Great question.
Yep.
Is there a circuit version or a vectorized version of your network that we can apply directly to PyTorch, or is it only through the framework that you provided?
It is currently only through the framework that we provided. But if that's something that you think would be valuable, definitely a project like that would also be something cool to come out of this hackathon.
You mentioned a trademark earlier. Does that mean at any point the algorithm is proprietary, or is it all open source?
So it's not all open source. We have kind of both a proprietary version that will get improved results. It's kind of the results of all of the personal experiments that we've done to build on top of these dendritic ideas. And then the open source version is a baseline that will also still get you significant improvements, but it doesn't have all the bells and whistles and all the secret sauce. But for this hackathon and over the next 2 months, you have access to both. And you can run experiments on both. You can see which one has more impact for you. And afterwards, we'll see about getting you more access. Okay, if there's no more questions, then it's time to start hacking. We'll be up here if you got questions you just didn't want to shout out in front of the room, and also we'll be available by Discord.
Just send the tokens around.
Oh, yes. Yeah, if you do want to use the secret sauce dendrites, that will give you a little bit better results. Just scan this QR code on the right. A link to the API is on the left. We'll also very quickly change this and add the Wi-Fi, add the weights and biases link, and anything else that people ask us about multiple times. We'll just quickly add it up here. All right, get hacking. Thanks for coming out.